Picture this. You're hosting a dinner party, you've invited 6 people, and you're just stressing about the whole dynamic.
Right. Who sits where? Will they get along?
Exactly. Will it be awkward?
Yeah.
Well, according to this stack of research we're looking at today on Ramsey theory, you can. You can actually stop stressing. Because mathematics literally guarantees that in any group of 6, you will have either 3 people who all know each other or 3 who are complete strangers.
It's the theorem on friends and strangers, and it's a perfect way into what we're talking about.
It really is.
We're looking at how order is not just, likely. It's mathematically inevitable, even in what looks like total chaos.
So this is our deep dive into a branch of combinatorics called Ramsey numbers. The core question in these papers is, well, it's pretty simple, right?
It is. It just asks, how large does a structure need to be before you can guarantee a specific pattern has to exist?
And that party example, R33, that's the easy one. The answer is 6.
Right, 6 vertices for a monochromatic triangle, so all friends or all strangers.
Okay, but what happens when you want, say, groups of 4? For R4, I mean, you'd think it might just double or something.
You would think that, but no, it triples.
Triples.
It jumps all the way to 18. You need 18 people in a room to guarantee that 4-person clique.
18. Wow. And this is where the research gets really sticky. Because the logical next step is R55. Right. We have supercomputers, we have AI. But all the papers are clear on this. R55 is, it's currently unknown.
We can't pin it down. We know it's somewhere between 43 and 46.
But not the exact number. Why?
Because it's less about raw computing power and more about the sheer complexity. It's not a linear problem. It's what we call a combinatorial explosion.
That idea of hitting a wall, it reminds you that sometimes brute force just isn't the answer. You need a smarter approach.
Yeah, absolutely.
Which is actually what our sponsor, Silk, is all about.
Yeah, that makes sense. You can't just throw processing power at a problem.
Right. Whether it's AI training or automation, you need to uncover where your agents can actually make the most impact.
So if you're looking to solve those kinds of complex problems in your business, check out embersilk.com for your AI needs.
So back to this mathematical wall. Why is R55 so incredibly hard? I mean, 43 nodes in a graph. That doesn't sound massive.
It sounds small, but the number of possible ways to color that graph, it's staggering. It grows at a rate of 0.2 to the n squared.
Oh, wow.
To brute force it. I think you'd be checking more possible graphs than there are atoms in the known universe.
That really puts things into perspective. It reminds me of that famous Paul Erdős thought experiment.
Oh, the alien one.
Right.
What?
He said if an alien force landed and demanded the value of R505, or they'd destroy the Earth.
We should marshal every computer, every mathematician, and just find it.
Because we could. It would take everything we have, but it's probably possible.
Probably.
But if those same aliens ask for the value of R6...
You attack the aliens?
Yeah. Your odds of winning an interstellar war are actually better than your odds of solving the math in time.
The complexity is just that steep, but, we aren't totally stuck. The recent papers are showing some huge wins, like they just verified R45 is exactly 25.
And they're not doing that by counting atoms. They're using something called SAT solvers, right?
Precisely. It's a shift from just raw calculation to logic.
So like a logic puzzle.
Exactly. Instead of checking every single graph, they use algorithms to prove that massive chunks of configurations are just impossible. It's like playing Sudoku on a brain-melting scale.
Speaking of brain melting, we have to mention Graham's number.
Oh, we have to.
It came from this very field of study as an upper bound for a related problem.
And it is so incomprehensibly large that if you tried to hold all its digits in your head, your brain would literally collapse into a black hole from the information density.
It just contextualizes what we're dealing with. We're kind of chipping away at the edge of infinity here.
We really are.
But, for me, the big takeaway isn't the difficulty. It's the optimism of it all.
How so?
Ramsey theory proves that complete total disorder is impossible. If your system is big enough, a pattern will always emerge.
That really is the beauty of it. Within a large enough system, order isn't just possible, it's inevitable.
I just love that thought. No matter how chaotic things might seem, the math says there's a pattern in there somewhere waiting to be found. Well, that's all the time we have for this deep dive.
If you enjoyed this conversation, please subscribe to the show. And hey, leave us a 5-star review if you can. It really does help get the word out.
It really does. Thanks for tuning in. Keep looking for those patterns, everyone. Catch you next time.